And as a continued discussion about application of this formula, let's consider a few simple cross-sections. Actually, even though I tell you that it's a few simple cross-section, I will mainly consider the rectangular cross-section, and then I'll consider this I-shaped cross-section. So let's first consider the simplest possible cross-section you can imagine, which is simple rectangular cross-section. And the cross-section has height of B, H, and the thickness of B. So this is cross-sectional view, not front view. So for this cross-section, and let's try to get QY, TY, and I, everything like analytically, okay, as a function of H and B and Y. So when you consider a location Y and try to obtain shear stress at Y position, what you have to do is you have to do QY integral, and to obtain QY integral, you have to do obtain the area for red block and red area, and you have to obtain the location for centroid for that red block. So regarding the centroid position, when you consider this red rectangular shape, and suppose that distance to the top of this red block is h/2 because the centroid is located at the halfway through, and the height of this red block is h/2 minus y. This is y. And if you consider the location for centroid, it will be y plus half of h/2 minus y, half of h/2 minus y. This is the height of this red block. So the location of this red one, centroid location for this red rectangle is by doing this summation 1/2 multiplied by y plus h/2. Now the area of this red one is h/2 minus y multiplied by b. Okay, so b times h/2 minus y. Now if you want to obtain qy, this integral is equivalent to a times the centroid position. So a is this, centroid position is this, and after massage this equation, you have something minus something and something plus something, which is very familiar expression for us, which resulted in h/2 square minus y square. Then after massage the equation, what you're gonna get is some constant, geometric constant bh square over 8 multiplied by 1 minus y over c square. Okay, so the reason why people like to massage the equation in this way is when y becomes c is h/2, then it becomes y over c approaches to 1. So this equation implies that y approaches to the top or bottom, so that y over c becomes 1 or negative 1. This equation becomes 0. When y becomes 0, this one becomes maximizes. So you can intuitively see when qy becomes maximizes, when qy becomes minimizes, and what will be the distribution of q over the y. It's parabolic distribution, right? Now if you plug in the expression for qy, and t is simply b, and I is 1/12 b h cube. So after you plug in qy, t, and I expression, tau as a function of y becomes this, and after canceling out h and massage the equation, bh becomes cross-sectional area, this guy. Okay, so you can do this by yourself. So tau as a function of y can be analytically expressed as 3b over 2a multiplied by 1 minus y over c squared. Okay, so if we make a graphical representation, tau becomes very small at top and bottom, tau becomes maximum at the center, and tau has intermediate size in the intermediate distance. And if you draw y and tau y relationship, when y is large or very small and top and bottom, tau becomes 0. When y equals 0, it becomes maximum, and in between you have parabolic distribution over y. Okay, so this is the application of the expression for rectangular shape. Now let's consider I-shaped beam, if you consider QI, you can see that QI increase much faster near the top compared to this rectangular shape where you see increase of Q quite smoothly. Here for I shape, increase of the Q near the top and bottom is really fast because when you consider area, you have a huge area as you change Y a little bit. However, below some point, even though you change Y, you increase of the area is relatively small. The increasing rate of QI becomes smaller. So QI distribution have like a something like this shape. Of course, QI distribution is symmetric because it has symmetric distribution over y larger than 0 and y smaller than 0 region. Now regarding the t, t is very large. Tau is proportional to 1 over t, but t becomes very small here. Okay, so if you multiply 1 over t factor here, when you consider tau y, tau y becomes very small due to large thickness at top and bottom, but tau becomes quite large in the middle, and this tau y is relatively more uniform than this distribution. Okay, and this is it. So for small t region, you expect quite large t tau xy. For small t region, you expect quite small tau xy distribution. But whatever cross section you are considering at y equals 0, qi becomes maximizes, and the tau xy becomes maximizes at y equals 0 or centroid position. Okay.